This is Little Dome Sea, one of the most remote places on Earth, 3,200 meters above sea level. Average summer temperature, minus 35 degrees Celsius. For 4 years, an international team returned to this frozen wasteland. Their mission, drill straight down through nearly 3 kilometers of solid ice. What they found will rewrite our understanding of Earth's climate. Trapped inside this ice are bubbles of ancient atmosphere, 1.5 million years old, the oldest continuous climate record ever recovered. Cambridge, England, August 2025. In a room kept at minus 23 degrees Celsius, Dr. Liz Thomas examines a section of ice core. This piece is from about 2,600 meters down. It's at least 1.2 million years old. When you get this deep and the ice is under this much pressure, it just looks like glass. The bubbles of atmosphere are so small, you can't even see them anymore. But they're there, waiting. Every cubic centimeter of this ice contains thousands of tiny bubbles. Each one a time capsule, a sample of Earth's ancient atmosphere sealed away before humans existed. Dr. Liz Thomas, head of ice core research at the British Antarctic Survey, said, "There is no other place on Earth that retains such a long record of the past atmosphere as Antarctica. It's our best hope to understand the fundamental drivers of Earth's climate shifts." Think of it as a library, not of books, of years. Every meter of ice compressed 13,000 years of snowfall, layer upon layer upon layer. 2,800 meters times 13,000 years per meter. Over 1.2 million years. Potentially 1.5 million, maybe more. The entire history of human civilization, all of recorded history, represents the top 6 meters of this core. Everything below that, a world before us. Why does ice preserve climate better than anything else? It starts with snow. In the interior of Antarctica, it never melts. Too cold, too high. Snow falls, accumulates, gets buried by more snow. Under pressure, snow crystals compress into firn, a transitional state between snow and ice. Then, deeper still, into solid glacial ice. As this happens, air trapped between the snowflakes gets sealed into bubbles, tiny prisons of atmosphere. Perfectly preserved. The dust, gases, isotopes, and chemical signals discovered could give clues to past climate and environmental changes, including wind patterns, temperatures, and rainfall. Inside those bubbles, carbon dioxide, methane, oxygen, nitrogen, the exact composition of Earth's atmosphere when the snow fell. Outside the bubbles, locked in the ice crystals themselves, isotopes of oxygen and hydrogen. The ratio of heavy to light isotopes tells us the temperature when the snow formed. Warmer climate, more heavy isotopes. Colder climate, fewer. Also trapped, dust, volcanic ash, pollen, marine algae called diatoms. Every speck tells a story. Marine sediment cores can go back millions of years, but they're imprecise, mixed by ocean currents, disturbed by burrowing organisms. Ice cores are different. Each meter of ice can contain as many as 13,000 years of climate data. The layers stay intact, undisturbed, continuous. A year-by-year record of Earth's atmosphere and climate. Until now, the oldest ice core was from a site called EPICA Dome C. 800,000 years. Impressive? Not enough. Because something happened about 1,000,000 years ago. Something fundamental. And we don't know what. Finding the right place to drill was the first challenge. You can't just drill anywhere. The team used radio echo sounding technologies to zero in on ice that might contain the time capsule they were looking for. The ice had to be thick enough to contain a long climate record, but not too thick. This can happen when the heat escaping from the Earth's mantle is trapped by a thick insulating blanket of ice. If the ice is too thick, we can lose the lowest and oldest layers of ice to melting, explains Dr. Robert Mulvaney of the British Antarctic Survey. Too thick, and geothermal heat from Earth's mantle melts the oldest ice at the bottom. You drill 3 kilometers down and find nothing. Water. Lost history. Too thin, and you don't have enough accumulation. The layers are compressed so tightly that resolving individual years becomes impossible. We needed a Goldilocks site. Ice thick enough for a well-resolved climate record at the greatest depth, but not too thick that the oldest ice had already melted away, said Mulvaney. They found it 35 kilometers from Concordia Station. Little Dome Sea. Ice thickness, 2,800 meters to bedrock. Elevation, 3,200 meters above sea level. Average summer temperature, minus 35 degrees Celsius. In winter? Don't ask. Perfect isolation. Perfect cold. Perfect preservation. The ice here accumulates slowly. Very slowly. Which means even thin layers represent long periods of time. Which means high resolution. Which means they could read Earth's climate year by year, going back over 1,000,000 years, if they could extract it without shattering it. The field team spent more than 200 days drilling and processing the ice core across 4 field seasons in the harsh environment of the central Antarctic plateau. 4 summers, 4 brief windows when drilling was even possible. At 3,200 meters altitude, the air is thin. Every physical task is exhausting. The drill itself is a masterpiece of engineering, electromechanical, designed to cut a cylinder of ice 10 centimeters in diameter. Here's the problem. Ice under pressure behaves differently than surface ice. When you get this deep and the ice is under this much pressure, it just looks like glass, Bass Ice Core engineer James Veal. At 2,800 meters, the ice is under about 250 atmospheres of pressure. Bring it to the surface too quickly, and the pressure release causes fractures. The core shatters. Data lost. Each 4.5 meter section of ice took around 2.5 hours to recover. Slowly, carefully. 2,800 meters divided by 4.5 meters per section. Over 600 sections, times 2.5 hours each. 1,500 hours of drilling alone, not counting setup, maintenance, breakdowns, weather delays. Every section had to be logged immediately. Depth, temperature, visual characteristics. Then cut into smaller pieces, recorded, photographed, stored in insulated boxes at minus 50 degrees Celsius. And they couldn't know if they'd succeeded. Not until they analyzed the ice. Not until they knew how old is the ice at the bottom. January 9th, 2025. The drill reached bedrock, 2,800 meters. The Beyond EPICA ice core drilling has finally reached the bedrock. This is a huge success for our project and for ice core science. The bottom 210 meters were different, heavily deformed, possibly mixed, maybe refrozen. There is even potential for yet older ice, dating back to the pre-Quaternary period, 2.58 million years ago, to be discovered within these base sections of the core. They won't know until they analyze it. But the upper 2,480 meters? We have a strong indication that the uppermost 2,480 meters contain a climate record that goes back to 1.2 million years, in a high-resolution record where up to 13,000 years are compressed into 1 meter of ice, said Chief Scientist Julian Westhoff. They had done it. The 2,800-meter ice core samples will now be transported carefully to Europe using specialized cold containers maintained under a strict logistics strategy. From Little Dome Sea to the coast, overland traverse. From Antarctica to Europe, refrigerated cargo ship. Every moment kept below -20 degrees Celsius. One power failure, one temperature spike, and 1 million years of data could be compromised. The core was divided among laboratories across Europe. British Antarctic Survey in Cambridge, University of Bern in Switzerland, Alfred Wegener Institute in Germany, CNRS in France. Each lab specializes in different analyses. Together, they'll piece together the complete story. The British Antarctic Survey's Ice Core team specializes in continuous flow analysis, a state-of-the-art technique that involves melting ice core sections ultra-slowly to simultaneously measure a range of chemical elements, particles, and isotope data. Continuous flow analysis, the gold standard. They take a section of core, 1 meter long, place it on a heated platform, and melt it, millimeter by millimeter. The meltwater flows continuously through a series of instruments, each one measuring something different. Instrument 1, chemical elements, sodium, calcium, dust particles. Instrument 2, isotopes, oxygen-18, deuterium. Instrument 3, particle count and size. All in real time, all at once. 7 weeks to melt and analyze 190 meters of ice, the oldest sections from the bottom of the core. As the ice melts, it releases everything trapped inside. Ancient dust, volcanic ash, and diatoms, which are tiny marine algae. Dust, wind patterns, aridity, continental weathering. Volcanic ash, precise dating markers. Eruptions leave signatures across entire hemispheres. Diatoms, ocean productivity, sea ice extent. The isotopes tell us temperature. More oxygen-18 relative to oxygen-16 means warmer snowfall. The ratio shifts with every climate swing. It was exciting to see the Ice Age as we drilled deeper, and especially when we knew we were drilling ice older than the EPICA record, which ended at 800,000 years ago, said Dr. Mulvaney. Warm, cold. Warm, cold. Glacial, interglacial. Glacial, interglacial. The rhythm of Earth's climate. But the real treasure is the bubbles. There are very little occlusions. The bubbles of atmosphere are so small you can't even see them anymore. At 2,600 meters depth, pressure has compressed them to near invisibility. But they're there. Other European laboratories will handle this part. University of Bern, CNRS, specialists in ancient atmosphere. They place ice samples in a vacuum chamber, let them melt. The bubbles release their trapped air. Instruments measure the composition with incredible precision. Carbon dioxide, parts per million. Methane, parts per billion. oxygen isotopes in the air itself. This is the data that changes everything. Because marine sediments can tell us ice volume, ocean temperature, but they can't tell us atmospheric CO2. Ice cores are the only direct measurement of ancient atmosphere we have. From the EPICA core, the 800,000-year record, we know that CO2 and temperature are tightly linked. When CO2 goes up, temperature follows. When it drops, ice ages begin. But that's only 800,000 years. What about before? This unprecedented ice core dataset will provide vital insights into the link between atmospheric CO2 levels and climate during a previously uncharted period in Earth's history, offering valuable context for predicting future climate change, said Dr. Thomas. Because something changed. Around 1 million years ago. Something fundamental about how Earth's climate works. And we're about to find out what. To understand what the ice cores revealed, we need to talk about why ice ages happen at all. It comes down to Earth's orbit. Serbian scientist Milutin Milankovic figured it out in 1941. Earth's orbit isn't perfectly circular or stable. It wobbles. 3 main cycles. Eccentricity. The shape of Earth's orbit changes from circular to slightly elliptical. Period. 100,000 years. Obliquity. Earth's axial tilt varies from 22.1 to 24.5 degrees. Period. 41,000 years. Precession. The direction Earth's axis points changes. Period. 21,000 years. These orbital changes alter how much sunlight hits different parts of Earth at different times of year. Particularly important, summer sunlight in the northern hemisphere. If northern summers are cool, snow from the previous winter doesn't melt completely. It accumulates, year after year. Ice sheets grow. If summers are warm, ice melts faster than it forms. Ice sheets shrink. Before the MPT, the glacial cycles were dominated by a 41,000-year periodicity with low-amplitude, thin ice sheets and a linear relationship to the Milankovic forcing from axial tilt. For millions of years, Earth's climate followed the 41,000-year obliquity cycle. Gentle ice ages, modest ice sheets, in and out of glaciation every 41,000 years. Then something changed. The Mid-Pleistocene transition, which occurred between 1.2 million and 900,000 years ago, marks the fundamental shift in Earth's glacial cycles. Between 1.2 million and 700,000 years ago, the rhythm changed. After the MPT, there have been strongly asymmetric cycles, with long-duration cooling of the climate and buildup of thick ice sheets, followed by a fast change from extreme glacial conditions to a warm interglacial. Glacial cycles became longer, colder, more intense. Instead of 41,000 years, they stretched to nearly 100,000 years. Ice sheets grew massive, covering Canada, Scandinavia, Northern Europe in ice kilometers thick. But why? Explaining this change is very difficult because there was no corresponding change in the orbital pacing that would trigger a change in timing. Earth's orbital cycles didn't change. The 41,000-year obliquity signal was still there, but Earth stopped responding to it. Over decades, scientists proposed mechanisms. Hypothesis 1. Ice sheets grew so large they became unstable, collapsing every 100,000 years regardless of orbital forcing. Hypothesis 2. Progressive removal of regolith, loose rock and soil, made it easier for ice sheets to grow on bare bedrock. Hypothesis 3. Ocean circulation changes around Antarctica altered heat distribution. Hypothesis 4. A progressive decrease in atmospheric carbon dioxide concentrations throughout the Pleistocene played a key role in triggering this major transition. Probably all of them. Together. Climate is a system. Everything affects everything. But which was dominant? What was the trigger? Marine sediments could show ice volume, ocean temperature, but not atmospheric CO2. Not directly. The 1.5 million year ice core will answer this for the first time. This record of 1.2 million years will give us several 41,000-year glacial cycles to compare with the more recent data from the original EPICA core, said Dr. Mulvaney. The ice core spans the entire Mid-Pleistocene transition. Before, during, after. Our data will yield the first continuous reconstructions of key environmental indicators, including atmospheric temperatures, wind patterns, sea ice extent, and marine productivity, spanning the past 1.5 million years, said Dr. Thomas. For the first time, we'll have continuous CO2 measurements through the transition. We'll see, did CO2 levels drop gradually before the MPT? Did they drop suddenly? Did they oscillate differently? We'll see how tightly CO2 and temperature were coupled during 41,000-year cycles versus 100,000-year cycles. We'll see if the relationship changed. We'll see wind patterns, dust transport, continental aridity. How dry were Ice Age climates before the MPT compared to after? We'll see ocean productivity, nutrient cycling, marine ecosystems. How did life in the oceans respond? This is a completely unknown period of our Earth's history, said Liz Thomas. We have theories, models, indirect evidence, but now we'll have data, real measurements, from Earth's own archive. And here's why it matters for our future. If we understand why climate sensitivity changed, why Earth started responding more dramatically to smaller orbital triggers, we can better predict how it will respond to the unprecedented CO2 levels we're creating now. The analysis will take years. Ice cores don't give up their secrets quickly. Dozens of scientists, hundreds of measurements, thousands of data points. But when they're done, we'll have something unprecedented. A continuous, high-resolution record of Earth's climate spanning 1.5 million years. Every bubble contains atmosphere that hasn't been breathed in over 1 million years. Air from a world before humans, before our genus Homo even existed. It's incredibly exciting to be part of this international effort to unlock the deepest secrets of Antarctica's ice. There is no other place on Earth that retains such a long record of the past atmosphere as Antarctica. It's our best hope to understand the fundamental drivers of Earth's climate shifts. The ice remembers. When we forgot there were ice ages at all, the ice remembered. When we lost track of CO2 levels, the ice remembered. And now, finally, we're learning to read what it's been trying to tell us. For 1.5 million years. This is Cosmic Canvas, where we excavate Earth's memory. Until next time, the past is not lost. It's frozen, waiting.